This NCTV episode will feature our technical manager for the metallurgy department, Andre. He will give you a practical tutorial of a ductile iron workflow scheme. So, Andre, 3 general tips to control your melt quality.
Yes, I would divide into 3 different topics. So, and I will start with spectrometer. Spectrometer is extremely important measurement in the foundry. Every foundry most likely have it, and we can trust spectrometer reading, except for carbon content. Carbon content is really specific. It's difficult to evaluate for spectrometer overall. So that is a little bit of a tip that yes, spectrometer is a must tool in a foundry, but be careful about carbon content. And if you go to the next one, it would be a temperature control. Temperature control is really important because a lot of defects are coming from temperature control. So, to give you an example, let's say if you have a high pouring temperature, therefore we will have definitely more defects in the castings because just a sheer contraction between pouring temperature and liquidus temperature. Anyhow, temperature control is extremely important to lower our defects ratio. And the last one, but extremely important, is metallurgical quality. This one is a little more hidden, so it's not so easy to detect it, but luckily we have tools such as ATAS, which is a metallurgical process control system, which helps us to detect this quality and improve it while we still have time. So before actually defect occurs, we can detect it with ATAS, and ATAS will give us by himself tips and tricks how to correct to avoid defects in the final iron.
What would you say are the most common mistakes in foundries that you visited that could have quite an easy solution?
Well, that's an interesting question. I would say through many years of visiting different foundries, the common mistake is that they think, or the theory they have is that more inoculation you add, the better quality you will have. But that is not actually true. What you can do is, if you do over inoculation, it's called, you can actually have a different defects. You can introduce new defects due to over inoculated molten iron. So that is definitely one of the tips and tricks which I have learned through the years with using our system, which is metallurgical process control, to detect the quality and to add only inoculant which is needed. So optimal amount of inoculant. If you over inoculated, it's not okay. If it's under inoculated, it's not okay as well. So over inoculation, it's not a myth, it is true. So that would be one of the biggest arguments to use our products to detect this and to have, let's say, a proper quality. The second one, I would say, goes really together. It's about magnesium content. And magnesium content as well is important to have it in a specific area. ATAS has a ductile iron optimizer, which gives a suggestion for amount of magnesium to add based on spectrometer information, temperature information, as well as calculation of oxygen in the melt. Oxygen combines with magnesium, so that means also we have to think about oxygen level in our molten iron. So these are 2 most common defects, or which we could find in the foundry. So I would advise everyone to think about these 2, and maybe in the future contact us and we will help them.
And you will show parts of this today?
Absolutely, and that is what I would like to show in the short presentation, how Novaka sees the production of ductile iron from step 1 to last one, which is from charging the furnaces to the final sample of ATAS and spectrometer. A practical tutorial of a ductile iron workflow scheme. On this slide, I would like to show you how Novacast sees ductile iron production with a scheme. So we have a time versus temperature, and I will try to explain each and every step with the different products in Foundry as well as Novacast products, how to do the proper way. So we start with the charging of furnace. In this case, we will talk about induction furnace. There is also cupola furnace, but we will focus now on induction furnace. So charging furnace with Metallmaster. So Novacast has a Metallmaster product, which is a charge optimizing tool. He always calculates based on materials you have in stock and attached prices to the lowest possible cost. So this is the main focus of Metallmaster, calculating charging materials to the lowest cost possible. There is also a different ways he can work. For instance, he can work with the from beginning. So if there is no heel or no leftovers in the furnace, or if we have some heel already inside of the furnace, which means in this case we have put it as a 100 kilograms. We also select a spectrometer reading, which they are connected to each other, Metallmaster and spectrometer. And since we have this information, he will adjust charge materials. We also see a target and results, what we will get if we charge with this amount of materials, as well as cost per kilogram, cost per charge. So now that we know how easy it is to make a proper charge to the lowest possible cost, we will go to the next step, which is charging. So operator receives a Metallmaster recipe, which means they have to look at it and adjust or add raw materials and other necessary materials into the furnace. So this is the whole process of charging and filling the furnace based on the Metallmaster recipe. So when we do this, then we have usually an idea of what temperature we should aim for after melting the charged materials. In this case, we have set it up to 1460 degrees. So operators are deslagging in order that they are able to take a temperature reading. The temperature reading is one of the key elements in the foundry, especially in the melt shop. So we have to be really careful to measure temperature as many times as possible. So operator has done his job. Now he waits for the temperature reading, and in this case it's 1468 degrees, which is close to what we would like to have. So good job. The next step is a spectrometer sample. So this is where normally every foundry is taking spectrometer reading, which means they take a molten metal with a spoon, they put it in some kind of a mold, depends what kind of mold, it can be copper mold and so on, to really cool fast, and they break it down, cut it, and then we have so-called coin. Then they carry this to the laboratory where the spectrometer reading starts. After this, we have the information in form like this, chemical composition, and this is a first reading from spectrometer. Also, we have to take an ATAS sample. This is a first ATAS MedStar sample to control metallurgical quality. So we can see that operator has placed a plain sand cap on a measuring unit. Then he has taken spoon, ceramic spoon preferably, flush it 3 times, and carefully pour into the plain sand cap with one steady stream. We see ATAS master has started to evaluate the quality, and first point, which is liquidus, it's directly connected to ACL, which is active carbon equivalent, and in this case it's out of the specification, which actually we would like to have. So ATAS, based on that information, gives us the feedback what kind of adjustment operator needs to do. So we have target is 4.09, actually is 3.99, so with addition of carb rises 2.35 kilograms. If the furnace has 2000 kilograms, we will have 4.09 carbon equivalent. And this is what we want to achieve. So now we go to the next step, which is called correction. And this is where operators look at the ATAS master screen. They see the amount of materials to add to adjust to the final active carbon equivalent target. So this is then the next sample. After this, we go into the process of heating. Sorry, we go to spectrometer. Once again, here we will take a spectrometer reading to check if everything is as it should be. And as we have seen before, same process, they pour a sample, take it to the lab, take spectrometer reading, and we can see that in ATAS as well. So then finally we go to the next step, which is ATAS MedStar, second sample, which means this is, again, we take it slowly. We do the 3-time flashing the ceramic spoon, and then we will put the molten iron into the plain sand cup once again. So we see the cooling curve. We have the ACL 4.09, which is what we wanted. And looks like everything is in a green zone, which means we have done the correct correction based on ATAS master. At the same time, when we are talking about the ductile iron production, ATAS also uses spectrometer information such as sulfur, silica, phosphor, and target weight, treatment temperature, to give you an exact magnesium content calculation, as well as steel scrap cover and inoculant addition. So this is extremely important. So usually sulfur, silica, and phosphor are grabbed automatically from spectrometer. Treated weight and temperature is adjusted, depends on the temperature reading and also on the accurate treatment weight in the ladle. We have to know that ATAS is calculating based on the oxygen calculation from the melt, exactly amount of magnesium to add. So now we are in this step, which means we will have a superheating of the furnace. Superheating has an effect of cleaning the molten melt. So this means that superheating deslagging, and finally taking the final temperature check. In this case 1504, which is extremely close to what we would like to see. So then we go to the next step, which is sandwich treatment. This means that operators has put materials from ATAS MedStar, which we see on the screen. So recipe of ductile iron optimizer, and they put it into the treatment ladle. After that, they have poured from furnaces into the treatment ladle, and the treatment started. So therefore we see this big reaction. The next step, we have slag skimming and temperature control. So as we see, operator is removing the slag and also taking the temperature. So this is a close-up of slag skimming. So this is important to have accurate temperature to see if we are in a range of 1365 degrees, around here. And finally we go to the spectrometer and ATAS MedStar final test. As we can see in the background, operator has just poured into the cup, plain sand cup, and also for spectrometer reading. So these two samples are the final step. We see here that MQ, which is metallurgical quality, is 92, which is great. Close to 100, 100 is maximum, so closer you are, the better quality you will have. The whole point of MQ is to evaluate which of elements are inside of green zone, or a process window we call it. If we are inside of process window, then we are sure that our production will be perfect. And same goes with spectrometer reading. We have to be in desired specification there as well. So this is our final step, as we call it. And I would like to invite you, if you have any questions, please do not hesitate to ask us. Send us a mail to support@novacast.se.
To summarize, what are the key benefits to have a workflow like this?
The key benefits are that if you use our products, Novacast products, which we just showed you, this will give you a best and the most accurate assumption of your quality in the melt, and therefore we can react before it's too late. So that is the most important. So our tools is some kind of a vision. So today you can see only this, but then if you use our products you can see wider. And if you can see, you can also react. If you don't see, you cannot react. That is the whole point of using our products, to have you inside of your quality and also to improve your quality while it's still time, so you don't scrap. So that is, I would say, the most beneficial.
The next NCTV episode will focus upon how foundries can evaluate how green they are and how they can reduce their environmental footprint by using our latest tool. Stay tuned.